Thank you for the introduction. And also I would like to thank the organizers for the opportunity to speak on this conference. It's my first time on Non-Hermitian conference, so I'm very excited to be here and talk here. Today I will talk about Klein-Gordon equation on discrete lattice. I'm not sure how this works. Okay, thank you. The organization of my talk is as follows. In the first two parts, it will be more like a revision and introduction to what is already known and what we need to know to build the model. In the third part, we will talk about some known facts about Klein-Gordon equation and what has been done by now. I will clarify some of my notion of crypto-hermiticity, what notion and terms do I use, and then I will apply this in a discrete model in one dimension of Klein-Gordon equation. So I will start with Klein-Gordon equation. More than 90 years ago, it was introduced by many scientists at the same time. So that's why it's called equation of many fathers. And it was introduced as a relativistic analog of Schrödinger equation for zero-spin particles. It consists of the Lambert operator and mass term multiplied by speed of light and divided by Planck's constant. And as soon as this equation was introduced, it also started to have many problems. First one is that for given momentum, the particle can have both positive and negative energies. This is often interpreted as the negative energies belong to antiparticles. Also, from the mathematical point of view, Klein-Gordon equation is the second-order differential equation in time, and that's why it has an extra degree of freedom. We need to know both psi and the derivative of psi of the wave function at the initial time. And the third problem I'm interested in is the problem with its probability interpretation. If we take the integrand of the zeroth term of current density, we get this conserved quantity which is indefinite. And that's a problem because we cannot identify it with a probability, and the integrand cannot be identified with probability density, so we don't know how to, well, we didn't know how to interpret it. The old approach to this problem was the approach with, of indefinite inner product. Well, there was introduced Klein-Gordon inner product. The reason why it has this form is that when we take scalar product, when we take Klein-Gordon inner product of a wave function with itself, we arrive to this conserved quantity Q, which was identified with the charge of the field, and its integrand, there's E, was identified with the charge density, which described the Klein-Gordon field. And because the Klein-Gordon inner product is indefinite, the Hilbert space can be split into those solutions which are positive, which has positive inner product, and those who has negative inner product. So as a physical space, we take the subspace with positive solutions, and there we can develop the physics. Also, this approach has some problems. For example, if you want to introduce some observable which mix the positive and negative energy states, you have a problem. Also, when you have some background, some potential time-dependent potential, then you also have problem. So what happened next? That there was introduced a quasi-Hermitian approach to this problematics. Its idea lays in the fact that, as I said before, Klein-Gordon equation is second order differential equation in time, and you can decompose it into two first-order differential equations in time. And you can write it as two-component Schrödinger equation. If you do all these new notations, you have two-component wave functions and Hamiltonian in a form of a 2 times 2 matrix, and which is also, of course, a non-Hermitian, as can be seen on the first look. And that's where the quasi-Hermitian approach takes place. Most of the work concerning this subject was done by Ali Mostafazadeh. Between years 2003 and 2006, there appeared many papers, mostly by Ali Mostafazadeh, but also by Znojil and Klein-Gordon and others. And here is the one of the results of the work of Ali Mostafazadeh, who constructed positive definite relativistically invariant and conserved inner product on the solution space of Klein-Gordon equation. There is like 5 articles by Ali on this subject. So if you want to look deeper on this stuff, I really recommend to read it. It's like 150 pages of interesting stuff. So this has been already done. What I'm gonna look into today is a little different approach. I will not consider I will look at a discrete approximation of Klein-Gordon equation, and for it, I will construct the metric operator and positive definite inner product, and I will make the assumptions more general. I will limit myself to the quantum mechanical framework only, so I will not try to make my inner product to be like relativistically invariant and so on. And before I do that, I need to familiarize you with my notions with crypto-hermiticity. Why I call it crypto-Hermitian operators? Why just another term for this stuff? Well, this term was introduced in 2007 by Smilga, and I think it nicely describes the truth under the crypto-Hermitian, quasi-Hermitian operators, and that's the fact that they are not really non-Hermitian. Their Hermiticity is only hidden, and we cannot see it because we look at them in the false space. And all we need to do is find the metric operator and introduce the new inner product in the secondary space where they are Hermitian. So that's why crypto-Hermitian. And the relationship between the two Hilbert spaces, the false one where our operator is non-Hermitian, and the second one where it's Hermitian, can be the difference is in the inner product, and the new inner product can be defined by means of the metric operator. Metric operator has to satisfy some conditions in order for the inner product to be well defined. It has to be Hermitian, positive, definite, bounded, and with bounded inverse. There are also some theories with unbounded metric operators. It's mathematically a little bit more complicated, and I'm not going to go to this here. And also I limit myself to bounded linear operators. So I will call them crypto-Hermitian if there exists metric operator satisfying these conditions, which defines this new inner product under which my operator is Hermitian. This can be rewritten also in this form. Crypto-Hermitian operators satisfy this Dieudonné equation or generalized Hermiticity equation, and it's also one of the possible ways how to find the metric operator that we are trying to solve this equation. They are also similar to Hermitian operators. The metric operator can be decomposed into this product of a similar invertible operator omega. I'm calling it Dyson's map, based on article of Dyson in 1961 or 56, something. And so by this map, we can map our non-Hermitian operator to even first another space, to isospectral Hermitian operator, and I'm denoting it small h. So in total, I have 3 Hilbert spaces, and I can formulate so-called free Hilbert space formulation of quantum mechanics. It's, this notation is based on an article by my supervisor, Dr. Znojil. You can read the article of the same name. It was published in 2009. So I have the false Hilbert space where it doesn't work, where it's non-Hermitian. The secondary Hilbert space where I've modified the inner product and my operator is Hermitian. And then I have the third physical Hilbert space. I called it physical because it's the one we know from classical quantum mechanical textbooks. The inner product here is the standard inner product, and our operator is Hermitian. And so to the problem of Klein-Gordon equation, review what I already said. I have Klein-Gordon equation in Schrödinger form, and this Hamiltonian H here, it's non-Hermitian, as I can see here. And I'm trying to find a metric for this operator. So this means I'm trying to solve the Dieudonné equation. Okay. I thought you had a question, but no, you were only, yeah. And okay, so I'm trying to solve the Dieudonné equation, which can be quite tricky for differential operators, and even for unbounded differential operators. So to make this problem more easy, I decided to discretize the Klein-Gordon operator, the Hamiltonian H, this one. And how I do it is by means of the finite difference method, which lies on, well, I do it as, I will discretize the spatial coordinate. I will split it in many equidistant points. And if I do this, I can express the Laplacian, well, which is in one dimension only, second derivative psi along x. Then it can be expressed asymptotically, well, not asymptotically, as this formula. And this is true for all the case. So if I split it into n parts, n points, then I can approximate the Laplace operator as n times n matrix. And this h here is the distance between 2 points. It's like how dense the lattice is. Okay, so this is the Laplace operator, and the operator k, if you remember, is Laplace plus m squared. So this is the operator k discretized. On the diagonal, I have this 2 plus m squared, and on off diagonals, I have -1. And for the sake of simplicity, I put the h equal to 1 here, because I'm interested only in the discrete case, and I don't want to do some continuous limit right now. This can be diagonalized. So it's similar to a diagonal matrix, k tilde, and on the diagonal, we have eigenvalues of this matrix, which is a tri-diagonal Toeplitz matrix, and the eigenvalues of it can be easily found in this form. And altogether, the Hamiltonian H in term of block matrices looks like this. So these are all zeros. There are A1s to AN, and here are only ones. And for this Hamiltonian, I will solve the Dieudonné equation, and the solution will look like this. It's a 2n parametric family of metric operators. The parameters need to satisfy those conditions in order for the metric to be positive definite. So the alphas need to be positive, and also this inequality between alphas and betas must hold. So I have quite a big freedom in all those parameters what to choose. And by means of this metric, I can construct the secondary Hilbert space where my Hamiltonian will be Hermitian. I can construct this new inner product, positive definite inner product, and it looks like this. So here on this secondary Hilbert space, I have unitary quantum evolution and everything works fine. And I can also introduce you to the Hamiltonian in the first space to make this picture complete. So that can be done by decomposition of the metric. There are more possible ways. This is decomposition by means of Kolesky decomposition method. We have another family of Dyson operators. It depends on 2n parameters, alpha, beta, e. And if we multiply the original Hamiltonian by this operator and its inverse, we get Hermitian Hamiltonian acting in the space HP, the physical one, which in this particular case is just Rn, R2n with the standard Euclidean inner product. So all of those Hamiltonians are isospectral to my original Hamiltonian. And yeah, that's it. I have 17 seconds, so right on time. There are some references. I wrote a little article in the proceedings. There are all those articles from Ali Mostafazadeh, and also some articles by Znojil and Kleefeld. So thank you for your attention. Right on time.
We have plenty of time for questions.
Just a curiosity, you discretize the Laplacian in a particular way. If you try some other numerical kind of discretization, you get similar results, or is not completely, is not of interest for you the way in which you diagonalize, discretize?
To be honest, I didn't discretize the Laplacian in any other way. What I saw in the literature, I've always met the Laplacian in this form. But maybe there are some other ways, and I didn't try it. I can do it in the future. Yes?
Can you take the continuous limit of your Hermitian Hamiltonian? It looks highly non-local. No? Have you thought about this?
Well, I wasn't successful with this yet. Yeah, of course, it's an idea to take a continuous limit, but yeah. Okay.
So why would you want to do that? Why would you want to get rid of the... So there's this very nice physics that you've just disposed of, which is particle creation in the Klein-Gordon equation. But I'm wondering, is anything still left of that? Is there still some sense in which you can get the Klein paradox, or that's completely gone now? Or is there some shadow of it left in this hermitized system?
Well, to answer the question why to do this is because like this, I have to really, okay, if you apply this quasi-Crypto-Hermitian theory to unbounded operators and use unbounded metrics, and you present it to people who does like deep mathematics, they will say that, oh, this doesn't work, and this is like, there are some problems you should think about, and there are some other problems. So in this model, there are no problems. Everything is bounded, and you can like nicely see the result. So that's why.
I make one other quick comment that Schrödinger also came up with the equation. In fact, I thought he was the first, but maybe that's what they say in physics classes.
I forgot to mention him in the first slide. Yeah, it said that he also formulated the Klein-Gordon equation in his notes, but then he was like,
before the Schrödinger equation.
It's not that good. Yeah.
So I would like to intervene since you raised this question. The equation you solve here is a wave equation for the so-called first quantized Klein-Gordon. She didn't solve the field equation. Only in the field equation will you see percreation. And Klein-Gordon is really not a wave equation. It's the Heisenberg equation for the field operator. Wave equation is always Schrödinger type. You can formulate quantum field theory in the Schrödinger representation. You can write down the Schrödinger functional, and you can ask all sorts of questions and to define positive definite probability distribution. But here you solved not a wave equation. I mean, psi square is not a probability distribution in field theory. You can, yes, but the question, what's the physical relevance?
Okay, maybe I interject for a minute and see if anybody has questions, and then we'll continue the discussion. Any other questions? Okay. If not, let's thank the speaker again.